Hi, welcome everyone. In today's video, I'm going to show you how to understand and make error correction equations and what are its implications. So I will try to make it a short video so that you can apply this model in your time series equations or panel data with long time periods. So we'll start the tutorial. We are working on error correction models, and it's also written as ECMs. So this model has a background as, so we'll start with, let's say we have an equation y is equal to alpha plus beta 1 x1 plus beta 2 x2 plus error term. So this is a time series data, so I can add t subscript here. So this is a time series equation. So typically this data should be long enough so that we can have time series patterns. For normality, people assume that it should be t should be greater than 30, but if you want to see the time period patterns, it should be around 50 minimum, so that there are some patterns that can be observed in the data. So if you have this data which is changing in time, first of all you have to check for presence of non-stationarity. So usually we apply unit 2 test so that we can check if the variables are I0 means stationary or I1. So this way we confirm the presence of non-stationary behavior. So if any of one of them is non-stationary or all of them are non-stationary, typically most of them are usually non-stationary, then what will mean is that in the presence of I1 variables, we will not be able to achieve the error term to be I0. We will not be able to get this, and we need to make sure that error term is I0 in nature so that the regression is not spurious. So the term that I introduced is spuriousness. The spurious equations are those which have few symptoms, like they have high t high t test values, high t values, so that the readers may assume that, wow, our equation is very good, the variables are highly significant. But the problem with spurious equation is that the variables may look significant, but it has a Durbin-Watson value smaller than r square. So high t values may lead to high r square and significant f test of the model, but the problem is because of the non-stationary nature, there is positive autocorrelation, which is leading to reduction of Durbin-Watson, and it is reduced to between 0 and 1 so that it is less than r square. So this is symptom that regression is spurious. So this may lead to the problem. So now we move towards detail. So we have confirmed that there is non-stationary variables, and there is a high likelihood that regression may be spurious. So we need to confirm how we can make sure that it is not spurious. So for that, first step is co-integration test. There are several ways to do it. For simple variables, we can use the Engle-Granger test for co-integration, or there are some other tests. I don't remember most of them names. Or there is the Engle-Granger test. Then there is Zivert-Andrews. This is a unit 2 test for structural weight, and it can also be used to check for co-integration. So there's Engle-Granger, and there are some other tests that are developed to check for co-integration. So if there is co-integration, then there is a hint that the regression is not spurious. So we have one hint. Now there is another way to confirm for regression to be non-spurious. That concept is called convergence hypothesis. Convergence hypothesis. So this says that if the regression, if the equation that I've shown above, that was y is equal to alpha plus beta 1 x1 plus beta 2 x2 plus e is not spurious, then any changes in e should be should lead to change in y, so that the equation is responsive to any explainable changes in e. So the hypothesis is that if this equation is true, then the next equation that I'm going to show should show some properties. So next equation is that as change in y, which is the first difference of y, is equal to beta 0 plus beta 1 change in x plus beta 2 change in x2. Okay, so and then we have minus gamma error term lag plus theta error term of this equation. So this is the specification for two-step ECM. In this two-step ECM, what we have done is we have estimated this first equation, generated the residuals, and checked if the residuals are I0 in nature. And this is also a process which the Engel-Granger equation uses. And then we created the lag for residuals and used as lag in this equation. And how to remember this equation? You have to convert the dependent variable into first difference form and all independent variable into first difference forms, and then add the lag of residuals. If this long run equation, this will become a long run equation because this is level form and this is first difference form. If this equation is not spurious and if it is converging, then this coefficient should be negative and between 0 and -1. So what does it mean? That if there is any increase in the error which is observable or even non-observable, if it is very for short time, it will be adjusted, because if the error is increased, then the resultant equation, if I write the resultant equation here, if I isolate the error term, so resultant equation is y is equal to y minus alpha minus beta 1 x1 minus beta 2 x2 equal to error term. So if error term is increased, so it should be corrected by a change in delta y, so that the answer equation is balanced. So if errors increase, it means this term is the difference between this and this is increasing. So what will happen is, if the equation is converging, then the difference must be reduced. How it will reduce? That y must reduce. So reduction in y can be seen as reduction is change in y. So if the equation is converging, then your coefficient should be negative. So this is the method of two-step ECM. Now, so if you are using a simple time series analysis and you are not expert in advanced time series models, or if you are doing a final data analysis with long time periods for each country and you don't know how to address autocorrelation, the fastest way is to run the long run equation like this. Okay, and then generate the residuals, check if they are stationary, and you need to know that if the variables are non-stationary, at least one of them should be non-stationary. If the residuals are stationary, you will convert it into first difference form and then add the lag of the residuals from the long run equation. And if the long run equation coefficient is negative, this should be negative, it will confirm that the long run equation is not spurious and it is converging. Means that any changes in the independent variable, any changes, what does mean by any changes in independent variable? If policymakers increase the x or x2, both have positive effect, as we seen in the equation here. So what will happen is, if this is increasing, so it will create a difference here, and that difference will be shown here. Okay, that difference. So if they are increasing, it means this difference is falling, means error term will be falling. So if error term is falling, so error term lag is falling, and the negative is negative coefficient is there. So negative becomes positive. So it means it will lead to a consequence that it will lead to increase in y. So if there is an increase in y, what will happen that this y will increase, and this gap which should be 0, because we assume that error term mean is 0, so which was decreasing to negative because of increase in these values, and in response to that this was increasing, and in response to that delta y is increased, and y has increased. So the gap which was reducing the error term is led to becoming 0 again because of the response in y. So this response is called the long run effect. Okay, and this long run effect only exists if the coefficient with the error term is negative. So this is called the error correction equation. So this is two-step method, and if you want to estimate using one step, you can run it like this. So you have delta y t alpha plus delta x beta 0 beta 1 delta x1 t plus beta 2 delta x2 t minus gamma error term, gamma rather now error term, you'll have yt minus 1. How we get it? I am just inserting the values of this equation in here. So minus gamma y minus 1 and minus beta 0 from the beta 1 from the long run, x minus t minus 1 minus beta 2 x t minus x2 t minus 1 x1 t minus 1 and plus error term vt. Now this is the one-step equation in which we don't have to generate the error term. Here the coefficient of this must be negative. Now the problem is here we cannot directly calculate the long run effect. So the long run effect is actually minus beta over minus gamma for variable 1 and minus beta 2 over minus gamma for variable 2. So this way you can calculate the long run effect if you have the one step ECM. So this way you can estimate. So the advantage of this model is that if you estimate one step equation, technically this error term will be stationary, and there are no these variables are already stationary because they are first difference, and this set of variables, even though they are non-stationary, but they are showing convergence. So this type of set of variables are jointly becoming E, which is I0 in nature, and if they are I0, then the coefficient will become negative. So an error term is already I0 in nature. So although equation has I0 variables, or if you go up in this two-step equation, this is I0, these are I0, these are I0, and this is I0, and this is I0. So this is a valid equation. So, and if it is not valid, let's suppose you have estimated the one-step ECM or a two-step ECM, one step or two-step ECM, what are the issues that can occur? It can still have autocorrelation. It will be shown using Durbin-Watson, but the problem is Durbin-Watson only looks at first order autocorrelation, so it is not reliable to use Durbin-Watson in the ECM equation. You use Grosh-Pagan test, which is available in Stata and eViews and many softwares. And if it is saying there is autocorrelation, what you can do is you can add more lags for these variables in the model. So you will add beta 1 2 delta x 1 t minus 2, so on. And how to check which variables, for which variable we need to add lags? So the criteria that I use is that if this beta 1 is significant, you need to add the lag, and if this is significant, you need to add another lag, and so on until the lags become insignificant. Or the fastest way is you use SIC or BIC criteria, and in many software these tools are available to identify the lag order criterion. In Stata there is command like VARSOC, vector autocorrection specification order criterion, that can help you to find lag order. This can be used, and this will help you to absorb if there is any autocorrelation. Okay, so and if this test is insignificant, it means the autocorrelation is solved, and you can use this two-step or one-step ECM equation for your interpretation. This will be your long run equation then, and this will become your short run equation. And this coefficient is very important, the convergence coefficient. And here you will have the variables according to the theory, and this theory will hold if there is convergence. I hope you understood the concept of error correction model, and you can apply this model in the panel data also. Only difference in the panel data is that when you estimate this two-step ECM, you have to convert this intercept into fixed effect or random effect so that it can absorb the cross-sectional unobserved heterogeneity, so that the model does not have any heteroscedasticity. And there are many other ways to absorb it. There are three competing models available in the panel data. One is called PMG, pool mean group, and then mean group, and dynamic fixed effect. These are three competing ways to estimate this error correction equation in the panel data. And you can do that manually by looking at the specification shown in the base paper, for the base paper where these models are discussed. Thank you very much for watching. I hope you understood how to create error correction equations and how they can be helpful in addressing autocorrelation in your data.